So, good morning. Today I'm going to talk about segmentation. First part of it. There are many parts, and the first part of today's lecture will actually be more about image formation, how the images, how the gray levels appear, and how to interpret them different ways. Then we are going to look at thresholding and how to implement this kind of segmentation. And in the end, I'm also going to look into morphological image processing filters and finally partial volume effects. So the usual one, we have our modules. If you want to run the notebook, run this one first, otherwise it will not work. So we have different applications. This is actually a pretty nasty one. We have an image here of the cortex, and it's about, the question is how to find it, but it's can be very tricky actually. And what we want to do is to separate the image into regions with some property. And it could be looking out for different phases in materials. We could look at filling holes, how holes are filled. Also segmenting fossils, or actually this one, which is an ugly example that we will try a couple of times during these lectures. The literature for this first part before the break is mainly John Ross, but also some information about ROC curves and how to work with those. So what we want to do with an imaging experiment. One part is the easy one, exploratory, looking at the images and see what we can get. Usually that kind of analysis is qualitative, but sometimes that's sufficient, but not that actually the aim of this class. Sometimes we don't know anything about the sample, we just make the images and see what we see. And sometimes we have already a hypothesis. But what we want to do is actually to test some kind of hypothesis based on the image data. So it could be how the temperature would affect the bubble size in some material, or how some gene change could have an effect on the bones, or if higher channel volume makes the bone weaker, and so on. So there can be many high-level hypotheses that we want to investigate. The first step is just looking at the exploratory part. We may have our idea of what the cell looks like, very schematic, but now we want to see the real stuff, and then it looks more like this. And from that, we need to extract the information, whatever we want to look at. And that's not so obvious as this nice schematic. And then we do our imaging experiment. Could be tomography. In this case, it's a big one, 2.5K cubed more or less, which deliver us 56 gigabytes of data per sample. And then we do some filtering and pre-processing, and we have seen already that filtering usually doesn't really put down the amount of data, but actually adds on, because you may not want to trash it directly. So the advantage of this filtering and pre-processing is actually that you have maybe still the same amount of data, but it's less noisy. But still, it's too much data to handle. So we want to reduce it in some way. And what we want to extract from the image is actually not just the gray levels, but we may want to see a volume fraction of something, or counting items like cells, maybe looking at the shape and the volume variations, and all that are things that we can measure in the images. But the first step is to do the segmentation. So that is how to identify relevant regions based on the gray levels, and in some cases also on the neighborhood. And typically start with the easiest, so Occam's razor is very important concept here. Try with the simplest ones. Could be that it actually works out, then go on with that. If you don't get the precision that you need, then you have to go for more and more fancy stuff. And sometimes you, with some experience, you see directly that, okay, that didn't work, then I need to go in that direction or maybe go in that direction. And we will look in the next 2 lectures about how to handle this problem. We already saw in the last lecture that images are usually not really what we expect them to be, so they are noisy and they are artifacts. And in the end, we have to add do some processing steps, and these steps hopefully makes it easier to segment the image. Ideally, what most filters are doing is that it improves, so we get maybe some 90% real signal and 10% bad signal. And in some cases, if your filter is bad, then you may actually trash all the good information and enhance the bad information. So that could happen, but that you should relatively quick capture. So we got an image from some modality. This is an X-ray radiograph of a rubber duck. And, well, rubber ducks are good. They are fantastic. But anyway, in this one has even a little piece of electronics in it. So you can see in this that there is the LED, there is some soldering, a PCB, and some batteries. And that is information that we can tell qualitatively what we have in this image. We can also look at the histogram. We see some distribution. This peak is the background around it, so it's actually not necessary to look at. And then you see that there is a dark part here, which I assume is related to the battery and the metal components. And then you have a pretty big region up in the bright, which is the main body. In between, you see maybe also that there is the skin, the contour where the rays goes through the skin. And yeah, that is what you can tell. What you also can look at is, for example, some morphometrics. You could look at the outline and trace it and describe it in some sense. So that is what we can do with this image to begin with. How you actually approach it depends on your background. Some people like algorithms, some people like actually a real world problem, and some people like data. So that's the different approaches you can add to go approach the problem. If you go the experimentalist, it's usually you have actually a problem, and then you do your images, and then you try to put some model or extract some relevant information. And the computer vision deep learning approach, you are more algorithmic data driven, and you look more into get and try to put it in that way. So it's more about the results that you extract. In some cases, or pretty many cases, you need to have a ground truth at least in the beginning in order to train your models and to tell actually what you can expect. Our basic model is that we have the system with some excitation. We have a sample that produces a response, and which is captured by the detector. And yeah, this is a bit repeat from previously. And looking at it in more detail, we may have our original expected sample image. That is what we put in the beam. Then we have some propagation through it. We have a beam profile. These two are actually the images or reference images from one of my detectors. It looks pretty crappy actually, but after normalization, you can get this nice image out of this combination here. And Then we can also look at different profiles across this rubber duck. And what you can see is the beam profile is pretty flat around here. That's the blue line. Then you have some overshoot, actually here after the normalization. And the orange one is what the detector gets. So there is a big difference in what the detector sees and what you actually should have. Actually, on this side, I have the detector intensity, and here I have normalized intensity. So that would be the green one is the normalized intensity. But this looks pretty good, but you see there is a little bit banded structures. In some cases, you can have a beam which is very looking more like Gaussian bell. Could also happen, and then you really need to normalize in order to get some good results. So let's look at Beer-Lambert's law, which is very common in particular in transmission imaging, where we have some input intensity, and then we have this exponential part here, which is in principle the thickness of the object and some attenuation coefficient. In practice, this actually turns into the integral along the ray. So the distance is sensing what's happening along the ray, and that is summed up into the attenuation effect that we have. And the important thing is actually to see that you have two components in this exponent, because they will give us some troubles, as we will see. So let's make a basic example. We have here 3 materials. We have material 1, 2, and 3, and they have some spread in alpha. Naturally, could be some natural material, different moisture contents, different mineralogy, whatever. And that gives you different spreads in the material. I create this model, and we get the detector signal out of it. And if we would look at an image captured from a sample that is following Beer-Lambert's law, what the detector sees is what you have here on the y-axis, which is very broad spread for low for high transmission, and the less transmission you have, the less sensitive you get. However, if you then compute the logarithm of this exponential, then the case actually flips around. So in practice, you have less bits to play with for the low transmission, and then in the end, you stretch it out too much more. And that is a problem when you start looking into the sensitivity analysis of your measurement. So typically, you want to be up in the upper part here, then you have good data. For tomography, recommendation is usually that you have at least 20% transmission, otherwise you come into the more uncertain region. So again, this rubber duck putting up normalization. A thing that we have in most detectors is a bias, because the AD converter converting the captured electrons into some digital value needs some bias to handle the fluctuations caused by noise. And that bias we need to subtract, and then we have a source profile and the bias again, and then we get the fully normalized image, which is pretty flat and nice in this case. Thanks to the normalization, we have transmission 1 means we are out in the void. If it's between 0 and 1, then we have some degree of attenuation within the sample. And if it's 0, that's in principle detector starvation, or the object is opaque. So if you put a lead brick in front of X-rays, you only see noise. You don't see any real signal. Just as a side note, if you put the LED brick in the front of a neutron beam, you will still see a flower behind it. So depending on the modality, you can have different sensitivities. Let's take a look at an example. We have mammography, something that is done pretty often in the hospitals. And coming back to the same equation that we had, typical images look something like this. This one has something bad in it, in the image. So that is what they want to detect, that there is some anomaly that we want to detect. Usually, or very often, it can be an indication of some cancer. And we make this model pretty easy. We only have two levels. We have air and we have breast tissue. And they have assigned different attenuation coefficients. And as we only have two values, actually the integral turns into just a sum. The product of the attenuation coefficient and the thickness. The basic model is just a sphere or half sphere. And that one is what we are going to use now in this example. Put different values. We have the attenuation coefficient, we have the pixel size, and we have the volume. And then what the detector sees is given by this equation. So that's in principle just a little bit NumPy with exponentials and sums. And the images we get, so this is the transmission image we see. So it's a side profile from this breast phantom. See, there is much attenuation in this area, and out in the void there is no attenuation at all. So this is, in principle, what an X-ray film would see. Yes, it's a negative. And if we look at the transmission profile, we see outside we have all transmitted, and then in the thickest part we have apparently about 90% transmission. Looking at the pixel distribution, we can see that we have, in principle, a linear effect here. That's just due to the geometry. And then we have many background pixels. So that is the kind of histogram we get from this image. And from this image, we can actually compute the local thickness. And then what we do is we compute the log of the normalized image and divide it by the attenuation coefficient, which we know in this case. That can be a science of its own to get the right attenuation coefficient. For constant values, for constant materials, it's easy. Then you can just make a couple of thickness measurements, see what the transmission is, and then you get this coefficient. If you have natural materials, the variations are much more, and then you should probably do a computed tomography to get it. So then instead, we get this profile. So we have a thickness image instead, and we see that the thickness at the thickest point is 10 centimeters, and then it goes down to 0. And of course, as we have flipped this curve, the histogram will also be flipped. And then we see the distribution of thicknesses instead. This kind of thickness computation is something that people do a lot at my beamlines, where we want to look at the thickness of water. Same principle, but just different beam. And looking at the thickness profile, the interesting thing is, if you remember original model, it was a half sphere, and now this is a kind of parabolic shape, and that is because we have we're going from in principle the first contact, so we're only looking in principle at the distances, and they can never be negative. So we are just looking through the shortest distance, and that's from 0 to some thickness. Now, that would have been the healthy case of this phantom, but it could be that the alpha is not constant, or there are irregularities in the shape, and that is what we actually are looking for in our radiographs. So if there is a lump, it would be denser than normal, and then it would appear with a different attenuation coefficient, and that is what we see. Now let's introduce this in our model. So now we add this material, a lump, which has twice the attenuation coefficient, and introduce it as a little sphere which is embedded in our other sphere. And if we start looking at that model instead, we can see, first of all, on the detector image, we now have this little bump in there. And looking at the histogram, originally it was this straight line staircase, but with the lump, we now have a redistribution of the gray levels in the histogram. And as this is denser, we have more material at the low transmission part, and that material is taken from somewhere, so we have a loss in this region instead. So this is just reshuffling the gray levels in the image, or in the histogram, sorry. And that would still be pretty tricky to do a detection on, but at least we see that there is a redistribution of the gray levels, depending if it's healthy or not. We can also do the same with the thickness, and the histogram will show you something that is still also a bit misleading from this histogram. So we have to do something else in order to detect this lump inside. Looking at the thickness profile of it, we now see that the thickness it looks like we have a different shape of this breast now, and that's not true. On the outside, you never see it directly, so this cannot be. That cannot have been that there is a shape change in this case. So there must be something else. The problem we see is actually twofold. In Beer-Lambert's law, we have two parts, two factors. One is the material dependent, and the other one is geometry dependent. And you can see exactly the same transmission value in one case where you have something that is denser, or in the other case, you have something that is just larger. And you don't know which one it is, unless you add a little bit more information to the conditions. And what you can do is changing the sample size. And originally, we have a round shape, but if we can change the shape into something flat instead, then you know that the thickness is constant, and every variation is a change in attenuation coefficient. The other option, and that's actually done in mammography, they use these plates to press the breast together, and then you have the same thickness. So that is actually what they're doing, so they remove this uncertainty with that. The other way would be to do to obtain 3D information, so doing, for example, computed tomography, and then you will see it anyway, because the computed tomography delivers actually a distribution of attenuation coefficients. So, what we do need is from the image formation, mostly you cannot just take the image and use it directly. You need to do some normalization, and the problem is that from transmission image, it can be difficult to interpret the content, in particular quantitatively. So, let's switch over to segmentation. And, oops, sorry. Just see, okay. What we want is to have this gray level image. For example, from this breast image, we want to have a new image which tells you have air, you have normal tissue, and you have some tumor tissue, and you want to identify that into few classes. The information we could have as input could be also RGB images, hyperspectral imaging, tensor images, anything. And in the end, we want to have maybe just a true-false image. It's there, it's not there. Or we may have few faces that we want to identify. With that reduction, we reduce our 32-bit image of 56 gigabytes into maybe a 1 or 2-bit image, and then we are down to about 2 gigabytes per sample, and that can actually be handled in a normal computer. 56, then you need pretty big workstation with a lot of RAM in it. So the basic segmentation problem, let's start with this test image. It's just in principle higher intensity cross in this image, and we added some noise. And we'll see what is happening with this image if we try to segment it. The histogram looks something like this. So you can already see that there is a big cluster of the histogram is here, and the smaller cluster is here. And from that, we can already start making some conclusions that probably the lower part in the high intensity is probably the cross. So that gives us already an indication where to put a threshold. And let's try. We could just put the threshold at 0.4 and saying everything greater is equal to 1, everything less is equal to 0. In Python, with NumPy, it's very easy. You just say you have your threshold, and then you just have your image and say greater or less, and you get it segmented already. So it's a very simple operation to do. So let's put it there. And with this 0.4, it was actually a pretty good threshold on this image. We get the cross very well marked out. And no, actually, there are some dark ones. This one, that one. Yeah, there are some misclassifications, but they're not so clearly visible. Actually, I should maybe change the colors a bit. So there are a little bit of misclassifications in here. But in general, we got the cross. So what is the effect of choosing different threshold now? So here I have a wild set of thresholds to apply. And if we have a too low threshold, you can see there is a lot of misclassifications. So that threshold was not too good enough. This one, yeah, it's still not good. And then going up, and until now, it's always false positives that we get. And then beyond 0.42, actually 58 is also pretty good. But if we go up to 74, you see that you have false negatives. So that was actually beyond what we should use. And yeah, at 0.9, we lose a lot of the cross. But it's always with an overlapping histogram that you have two classes that statistically overlap each other. You always have to make some compromise, and you have to decide if you want more false positives or more false negatives. So let's look at a real example. Here is an image of some cells. The histogram is not so easy to interpret. We have a big peak, which is just the background, and then we have all the dark spots. They are distributed along this long tail, so there are no distinct point where we can put our threshold. So then is the question how to put a threshold, and let's try the same thing as we did before. We set different levels. Here we have 100 up to 200, and what you can see is here you lose quite many of the cells in this corner. Still, this one may be okay. And when you increase the threshold, you can see that there is really a trend diagonally from the upper left to the lower right. And the reason for this diagonal is that maybe you can see that there is a gray level gradient in the image which goes diagonally. It's maybe not so easy to see in the daylight, but on your screen you can check this. And that makes it hard to set a threshold, because a threshold assumes that you have the same level. And that can also be illustrated with this plot, which would kind of correspond to a flat image where you have a lot of cells. You put the threshold and easily detect everybody. In the case that we have this background gradient, you can see that the intensity is following, and a cell which is in the lower part is detected differently than a cell in this upper part. And that has an impact then if you want to quantify the cell sizes or even the cell count, that you will have actually larger cells in one corner than in the other corner. So this is something you really need to watch out for, that you have a flat background, or that you compensate for in homogeneous background. Then we have other types of images. We don't have to just have scalars, so let's look at some kind of vector valued data. In this case, we have the coordinates, we have a detector value, and then we have some kind of orientation vector in x and y. Looking at that, you can look at something called the collocation histogram. It's something that you can get from Seaborn package. So it's a plotting package that you can use, where you just put in a table and it plots all combinations with each other. And well, the first two are pretty boring actually, because it's x and y coordinates, so they should map just like a gridded matrix. And then you see different combinations. The fun thing is that if you look at two vectors against each other, you can see that they actually plot a circle. In some cases, you can see nice trends if you do this kind of plot. Other cases require some interpretation. But as an overview, this kind of plot can be helpful if you have multidimensional data. If we plot this as a vector field, you can see that these vector arrows, they are colored with the intensity, they get a position, and they get an orientation. And this is what we want to segment now. And there are many ways. You can say that if, for example, the x component is beyond a quarter and the y component is beyond a quarter, then we should segment it as a 1. So that would be this corner region here. So that's pure geometry. But we can also look at other things, like the vector components, and select those for our segmentation. We can also looking at orientations and looking at the dot product of the different, and just seeing here the x-axis component. We can also look at the orientation, so looking at the angle and saying that the angle needs to be within some range. And that can give us, oh, I thought I should have images on this. I have lost them somehow. That was strange. Let's see. No, that wasn't meant to be. No? Oh, yeah, that wasn't meant to be apparently. Yeah, I thought there should be some images, but they don't want to appear for me today. I'll check in the break and show you later. They should be in the lecture notes anyway. sometimes when I jump in the middle, then it goes a little bit, some information is lost. Yeah, that one is lost now. Yeah, so this brings me to the end of the first part. So thresholding is one way of segmenting, and it is also the first one. It's very easy because you can usually get an indication from the histogram where to put the threshold. Can of course also work with a slider, for example in ImageJ, and see where you get a good value. And to do it well, you need to always have a flat background. Normalization is very important for the segmentation. And if you have non-scalar values, they can also be thresholded, but your thresholding model will be a little more tricky. I never did any segmentation now in this lecture on the breast phantom. That one would require some more normalization in order to make that possible. Because as you saw, the histogram didn't reveal really any information. So in principle, if you would put a single threshold, the thickest parts of the breast would be same as a tumor, so most of the breast would be a tumor. So that doesn't make sense really. So for that, you need to have some better choice or play with the geometry so that it's possible to make it a measurement. So that was a quick first part actually. I'm a little bit ahead of time. Let's make a break. Should we say till 5 past? Then we can continue.